So, ladies and gentlemen, let me welcome you in the morning session number 5. This session is devoted, according to the titles, I assume, to aggregation operators. We have 4 talks. So the first talk is focused on the construction of uninorms on bounded lattices via other uninorms. The speaker is Charlie, Denis Gilchari. So please take the floor.
If any two elements have a supremum and infimum, for the elements A and B, this symbol implies that A is smaller than B. If A is smaller than or equal to B, or B is smaller than A, these elements are called comparable, and we use this notation. Otherwise, they are called incomparable, denoted by this symbol. Here, we define some sets used in this paper. This sets denotes all elements incomparable with A. We denote by this notation the set of all elements incomparable with A and B. Lastly, the set denotes all elements incomparable with A but comparable B. A lattice is called bounded if it has bottom and top elements denoted by 0 and 1 respectively. In this paper, we denote by L a bounded lattice. We can define the closed subinterval of L like this. And this closed interval is a bounded lattice with the top element B and bottom elements A. Similarly, we can define other subintervals of L. A binary operation U is called a uninorm if it satisfies increasingness, associativity, commutativity, and it has a neutral element. If for all elements in a bounded lattice L, this equality is provided, then it is called an idempotent uninorm. If this equality is satisfied, U is called an conjunctive uninorm. And similarly, we can define a disjunctive uninorm. If the neutral element E of a uninorm is 1, we have that a T-norm. Dually, the neutral element is 0, we get a T-conorm. In the following, we can give some examples of T-norms and T-conorms. The restriction of a uninorm on the closed subintervals 0, E and E1 are a T-norm and a T-conorm respectively. We denote by this notation the class of all uninorms on a bounded lattice satisfying this condition. Similarly, we can define the class of UMX. Suppose that K is an element L different from 0, 1, S is a T-conorm, U prime is a uninorm, and the operation UL is defined by the formula 1. In that case, we have that if U prime satisfies this condition, then UL is a uninorm if and only if this statement is provided. If an element C incomparable with K exists, then UL is a uninorm if and only if these statements are provided. We can demonstrate the structure of a uninorm by this figure. In the following, we show that this condition is not necessary for this function to generate a uninorm. Considering this bounded lattice and the uninorm U prime defined by table 1, then we can see that for the elements m smaller than e and L incomparable with A, the value of U prime is m smaller than e. And if we apply the construction method in theorem 2, we can obtain this uninorm. If we take in theorem 2 E is equal to K, in that case we have a T norm and it satisfies this condition. In this case, we obtain a structure of a uninorm presented by the formula 2. Here, if considering drastic T conorm, then we get that a uninorm defined in this paper. If taking E is equal to 1, then we get a T conorm, and it is also satisfies this condition. In this case, we have a structure of a T conorm defined by the formula 3. Here, if we consider supremum T conorm or drastic T conorm on the closed subinterval K1 or 0K, then we have some existing T conorms. Considering these bounded lattices and the uninorm U prime defined in this table, based on the construction method in theorem 2, we can obtain this uninorm when considering a drastic T conorm. We should note that our construction method does not have to coincide with some existing uninorms introduced in this paper. We still take the lattice L2 and the uninorm U prime given by table 3. If we apply the construction methods in this paper, we have this uninorm, and it is different from our uninorm. Similarly, if we use the construction method in this paper, we obtain this uninorm, also different from our uninorm. And considering this uninorm, we have it is a disjunctive uninorm. If K is equal to 1, then it coincides the uninorm U prime. It is the class of U max if and only if the uninorm U prime is in the same class. In general, it is not an idempotent uninorm because for the elements incomparable with K, its value is 1. On the other hand, if we consider that the set of all elements incomparable with K is empty set, supremum T conorm and U prime is an idempotent uninorm, then UL is also idempotent uninorm. In the following, we propose a dual construction methods for uninorms. Suppose that T is an element in a bounded lattice different from 0, 1. T is a T norm, U double prime is a uninorm, and the operation UL is defined by the formula 4. In that case, we have that if U double prime satisfies this condition, then UL is a uninorm if and only if this statement is provided. If an element incomparable with T exists, then UL is a uninorm if and only if these statements are provided. We can demonstrate that the structure of the uninorm in the above theorem by this figure. If we take in the above theorem E is T, then we have a T conorm satisfying this condition. And we have a structure of a uninorm presented by the formula phi. Here, if we consider drastic T conorm, then this uninorm coincides with the ones defined in this paper. If we take E is 1, in this case we have a T norm, and then we have a structure of T norm in given by the formula 6. Here, if we take infimum T norm or drastic T norm on the closed subintervals 0, T or T1, then we obtain some existing T norm. And if we consider this uninorm, we can see that this uninorm conjunctive, and if T is equal to 0, then it coincides with the uninorm U double prime. If it is in the class of U mean, if and only if U double prime is in the same class. In general, it is not idempotent uninorm because an element incomparable with T exists. Then we have its value is 0. On the other hand, it is an idempotent uninorm if and only if we consider that the set of all elements incomparable with T is empty set, infimum T norm, and U double prime is an idempotent uninorm. This is references, and thank you for your attention.
Thank you very much for the talk. There are some questions, remarks. No? No questions? No remarks? Maybe I have one. So there are some constructions method, for example, ordinal sums. Also, there is some definition of ordinal sum for uninorms. So maybe there is a possibility to express your construction using this technique. Yeah, because I see that you use some uninorms in the construction, and now there was one problem that if we constructed ordinal sum of uninorms, we need to change like the ordering on the lattice somehow. But here is still the same ordering. So therefore, it would be interesting to look at that definition or method, and maybe to find how it works like this, and why not in the general case. Yeah. So other questions, no remarks. So thanks once again. And now I would like to introduce the second talk. The speaker will be Mirko Navara, and the talk is focused on the approximation using triangular norms. Please, Mirko, take the floor.
Morning, ladies and gentlemen. I'm going to present joint work with my former students, Alexei Popovich. And the task was to find a T norm which approximately fits to given data. Given data mean that we are given two-dimensional points and values at them which should be followed as much as possible, not necessarily exactly. So we have a sequence of triples and we have to fit it to them. More exactly, we have a criterion, well, usual one, to minimize the sum of squares of differences at all nodes, or equivalently, the square root of this, which has somewhat better meaning, but the same solution. And we may expect the data satisfy the inequality, which is satisfied by all the t-norms, so that the desired value is not greater than the argument. But because of imprecision of the data, we can also consider exceptional cases when this is violated. It's not so important, but usually let's think that these data can be values of some t-norm at all. And for that, this inequality is needed. So one approach is to restrict attention to one parametric family of t-norms, say Frank t-norms are a good example. And we have just to tune one parameter, and there are standard optimizing methods for that. So it seems to be quite an easy and usual task. It's not so easy. The surprising fact which we encountered is that the dependence is not unimodal. It doesn't have a unique local minimum. And this is a typical shape which we encountered, so that you see that it's composed from several pieces. And while we would agree that we have found a minimum here, it's not the global minimum. So it's not as easy, and it requires some further attention to find the global minimum, really. But I will not speak much of this case. I will speak of the more general case when we do not restrict to one family of t-norms, but we consider, say, all t-norms. Okay, this is a very difficult task. So we will restrict. Let's speak of strict t-norms or nilpotent t-norms or both, not others. And the advantage is that we can use its additive generator, alternatively multiplicative generator. I will speak of additive generators. They attain values from the closed interval from 0 to infinity included. It's decreasing, and the t-norm can be expressed this way. And now we do not have to optimize a two-dimensional function, but a one-dimensional, a unary function. That's somewhat easier task. So now we want to optimize this unary function. The good news is that it's monotonic. So that seems to reduce our task to something simpler. The bad news is that the dependence is hardly interpretable. That means if you want to express the dependence between the t-norm and its generator, you usually do not have any idea how they are related. And I'll have a second talk on Thursday when I shall deal with this problem in more detail. And I hope I will persuade you that this is the case. So regretfully, when we change the generator, we don't see what happens with the t-norm. And the problem is because the generator occurs here, but also here as its inverse. So when you change something, you change something else, and it's difficult to have it under control. Another bad news is that monotonic approximations are not standard task in numerical analysis, because usually the methods are linear. That means a linear combination of inputs creates the same linear combination of corresponding outputs to separate parts, components. If you agree on that, you cannot guarantee monotonicity. So when you want to have the dependence monotonic, your choice of methods is restricted to something which is on the boundary of the interest of numerical analysts. But there are such methods. Another bad news is that we need the inverse of the generator. And many approximation methods are such that the inverse can hardly be computed, possibly not a closed formula, so that you need some numerical methods to find it. It makes problems. So it's not as easy. And that's what I'm going to talk in the whole rest of this presentation. Belyakov. Belyakov presented an algorithm which solves this problem. Before that, he dealt with monotonic approximations. So with that background, he felt prepared to solve this task as a byproduct of his effort. And he did it, yes. So his approach says, transform the goal, because you can apply the unknown generator to both sides and say that your approximate equality means that the sum of generators on the arguments should be approximately the sum of generators at the desired value. And here, this way, you avoid the need to use the inverse, and one obstacle is overcome. Good trick. Well, known trick, used many times. Then choose several nodes independently of where the data were given. Simply split the whole domain to some segments by choosing nodes not related to the data, just used for the approximation. And then interpolate values of the generator on these points. The last one being that the value at 1 must be 0. That's obvious for the additive generator. So that's the last node. And approximated in the simplest case by a linear spline, by piecewise linear function. Well, then monotonicity is not a problem. More generally, you can consider higher order splines if you pay attention to keep monotonicity. That's also a possible alternative. So after this, the task reduces to choosing the values at the node monotonically in such a way that you optimize the fitting of the generator to the data. And these values will become the values of the design generator, exactly because it's an interpolation which goes exactly through these points. So this is a task which was simply solved by methods which Belyakov developed for other purposes. Now, what are problems of this? First of all, the generator is determined, additive generator is determined only up to a positive multiple. So that you can multiply it by anything. First of all, there is no starting point. Where to start? It can be everywhere. And if you make the generator very small, the criterion will be also very small, tending to 0 in the extreme case if the generator is so small that it goes to 0, almost. So that's not desired. Well, solution is fix one point and look only at additive generators which go through this point. Each genome with an additive generator has one which goes through that, so it doesn't restrict the solution. And then we can go on. So one point will be fixed, the others will be subject to optimization. Satisfactory solution. The next problem is that the value at 0 for strict genomes must be infinity. Of course, not subject to some linear approximation and spline interpolation and such standard methods. So you need to use something else. The choice is use some other function which goes to infinity, say the reciprocal function, and use this in some small neighborhood of 0 instead, and then continue with the usual interpolation. By the way, choosing exactly this function as Gleb-Belyakov did it is a rather exotic solution, and the generators which tend to this shape near 0 are rather rare and strange. So another choice should be considered, but we did not extend our research in this direction so far. A combined solution of the task on this slide is as follows. First, take some small epsilon near 0. Fix the value in it, say, to 1 without loss of generating. Replace by some function like 1 over x in the neighborhood of 0 for smaller values than epsilon. And from now on, go from epsilon to 1. Use a spline, possibly a linear spline, which could be satisfactory, going through the points where the first arguments are chosen and the seconds are subject to optimization, yes, the values in them. And for this epsilon, Belyakov have chosen the smallest value in the data. Not a surprising choice, almost well motivated. He says that the values of the generator for smaller arguments than epsilon are unimportant, so he didn't care to replace it by some other function, saying, I will not evaluate it there, so why to take care? That's not, his argument is that this epsilon is the smallest of all the desired values of the t-norm, which are usually smaller than the points where we evaluated it. So it's the smallest positive number among the data. So that's an argument why he has chosen this. We do not complain, okay? But the values of the generators can be important because in this we want this expression to be approximately this. And of course, first of all, if you have data without any restriction, anything can happen. We can have some data which are maybe nonsense, but still accepted because of being not values of any t-norm, but still input values. And second, you have a sum of two values which can exceed any value in this. So that's a problem that, in fact, we can deal with some values which are smaller than this chosen epsilon. And we cannot avoid it. So that's one problem which we pointed but did not solve. That's a possible way of future research. There is another criticism that Belyakov optimized the additive generator. It's not the same task as optimizing the t-norm itself. Because the original criterion, which was naturally sum of squares of differences of the t-norm from the desired values, was replaced by the sum of squares of differences between the values of the additive generator. But somewhere these values are big, therefore they have a big influence on the criterion. Somewhere they are small, and the influence is low. So that Belyakov, in his approach, distorted the weights of separate contributions to the criterion, and therefore he got something different. He got an optimization of this criterion, which is not the optimal solution of the original criterion. So we tried to compare. First of all, it's needed to suggest some alternative. One suggestion is, okay, let's go back to the original criterion and try to optimize it using the values in the nodes. That means these are the values of the intended generator in the node. That's possible, but it's much more complex. It's a difficult task. So exceptionally, we can afford to solve that, waiting for the result until it's optimized in many dimensions and with many computations, including even this inverse of the generator. So that we can make it for comparison, but it's not of practical use. And we suggest an alternative which is feasible, and that is, let's change the weights of the data so that we eliminate the distortion caused by the principal. So we predict how much the influence is changed by the looking at the generator, and we compensate it by using such weights which give almost the same influence to all data, almost the same influence on the original criterion. The advantage is that the complexity is almost the same. We just compute this expression and include it as a weight in the optimizing algorithm, which is not a problem. Now, what is obtained? Experimental verification of that. So you see, in order to know how good it was, we used artificial examples where we have taken different t-norms, known t-norms, so that we knew the desired solution. We generated data, added some noise, and we used the Belyakov's algorithm, original, our proposed algorithm, and the ground truth, because we knew what should have been the solution. So we use this for different number of nodes and different size of data sets, artificial synthetic data. And you see that now this is the root of mean square error. So if it's twice better, it's substantial. And you see, yes, we have our criterion applied, the original criterion which should have been optimized, was reached much better. You see that almost all, except for the last line, were better and substantially better than the results obtained by the Belyakov's method. So the conclusion is, yes, we can improve it substantially. And we can get better results by this small modification of his algorithm. Now, graphically, in the horizontal line, you have the desired value in the horizontal is vertical is the correct value, and horizontal is what was obtained as the value of the t-norm in the node. In one point of the data. So optimally, we should be very close to the diagonal. And we are. Well, the Belyakov's method has much more variance around it, as you see. You also can see that there are some features due to the choice of nodes. You can see where the nodes have been chosen and where the errors are bigger. And you see that both methods have problems near zero. This is the worst optimized piece, possibly because of that strange choice of the reciprocal function. Another such picture for bigger set of data, and you see that our approach was again graphically much better than the original, so that we proposed an important improvement, substantial improvement, without requiring much bigger computational force. Thank you for your attention.
Thank you very much for interesting talk. There are some questions, remarks. Irina, first.
Late, and therefore I missed the general problem. Yeah, and therefore, so I'm curious. Yeah, so big efforts. Yeah, what for actually? Yeah, because t-norm, yeah, as we know it, is used mostly as an operator. Yeah, and so of course you can use it for approximation, for example, as some atomic function. Yeah, but this is not its primary purpose. Yeah, being introduced, and so.
We want to choose a t-norm which fits to empirical data. Maybe we have a human expert solving the task. We ask him, what are you doing? Okay, we collect data from real work, and we want to replace this person by an automaton. So we collect data and we want to imitate his action, thinking that he combines several inputs by some operator, which could be a t-norm because it's a conjunction of some fuzzy values. Okay, we collect data. We want to model it by t-norm. The t-norm is not given to us. Let's look for that.
Yeah, so this means, yeah, so I can only repeat the question, yeah, because this is, as it is formulated, is a typical regression problem, yeah, and therefore, so this problem can be solved, yeah, with various regressors, so-called, yeah, and for your solution, yeah, you selected this exotic, say, yeah, regressor. So I repeat only my question, why? Thank you.
Another?
As a generic question, it's very difficult.
So please
to solve.
use that.
We propose a feasible solution. So far, we are aware of two, Belyakov's and Wow's.
Thank you very much for the presentation. It was very interesting. I have one question. I don't know if you're familiar with the problem of the completion of the norms, in which you know a piece of the generator and the rest can be determined uniquely or not. Have you considered the possibility of determine only a piece of the generator and then complete the rest using the structure of the T-norm?
Well, complete the rest, that's a difficult point. You suggest something, and at some moment you are supposed to compute the inverse on values which you did not cover with that piece. So that having a piece of the generator, you cannot evaluate this expression at some point. You need the whole generator in order to speak of the values of the T-norm. Otherwise, you miss some piece and cannot continue.
Okay, thank you.
Okay, Radko?
So we were inspired by Gleb, but Gleb did also, of course, the similar story with copulas, with Archimedean copulas, to tell the truth. And maybe to answer to Irina, for T-norms, I agree with you. For copulas, it's very common that you have some observed sample and you try to fit some model, and which is usually the stochastic dependent structure done exactly by copulas. So maybe you can continue in your approach also for copulas, of course, adding only convexity of additive generator. And the other thing, why we are always on continuous Archimedean, we can go also, of course, to continuous. And in some sense, you have to determine the idempotent elements and to continue in your approach. And maybe what could be for you interesting, but maybe you know that we know that each continuous T-norm continuous can be approximated by either strict or nilpotent, what you choose with arbitrary in advance chosen precision. So maybe such ideas could help also you in your further research.
I would say that doing it for all continuous T-norms could be a possible next step. But it cannot be done without a satisfactory solution of this step. It obviously must be based on a solution of this task first. And yes, but if you want to optimize a continuous genome, at some moment, at some piece, you will need an ordinal summand, which will be strict or nilpotent, and you will need to solve this as a subtask. So without having this as a basic stone, you cannot build, yes, without this brick, you cannot build a wall. So it's necessary to do this. And as concerns copulas, I think that that task is in some sense easier. In some sense, yes, it's a different task and different ideas can be applied. The problem is that we studied associative operations, and associativity is difficult to keep. The generators are the way how to get. Okay, if we agree on associativity, we have difficulties with the binary operation, but we can switch to a unary operation. If we look at copulas, ignore associativity, okay, that's a completely different task. In 2 dimensions, without this tool, but without these restrictions. That's something else.
Thank you very much. Time is running, so and now we will continue with the third talk provided by Miriam Kleinova. And it's focused on the maximal chain as a tool for generalization of the discrete Choquette integral. Please take the floor.
Today I will talk about the generalization of the Schocker integral via maximal change. On this topic, we have worked together with my supervisor, Andrej Hutnik. Most discussed results we can see, or you can see, in our recently published article, Maximal Chain-Based Schocker-like Integrals. Okay, we will start with the standard formula for the discrete Schocker integral, which is defined with respect to games. It is the set function which is grounded, and that means that value of the game in empty set is equal 0. On the formula, we can see two interesting points. The first one is permutation, which rearrange input vector in non-increasing way. And in the second is set A with below indices X and sigma. These sets create a maximal chain, which sets have this form. In the article of Honda and Köppen, one can find a slightly modified formula for the Schocker integral, where authors emphasized that the permutation is tied with input vector x. This idea they extended, and they considered input vector y. Firstly, they rearrange vector y in non-increasing way, and then this permutation was used for input vector x. This idea motivated also us, but we consider a basic set, two-dimensional basic set x and constant vector y. Then it is easy to see that there are two possible permutations which rearrange vector y in non-decreasing way, and therefore we have two possibilities how to compute Honda's functional. But if we consider non-constant input vector x and gain or the weakest normalized capacity, which value is only here 1, and here we have 0, and here also, the formulas 1 and 2 can differ. We also observed that the value of the Honda functional doesn't depend on induced vectors. That means that, for example, for three induced vector y, y1 with element 3, 1, 7, y2 with elements 2, 0, and 10, and y3 with elements 15, 4, and 22, we have the only permutation which rearrange all three induced vectors in a non-increasing way. Therefore, also sets which are in the formula of Honda's functional are the same for any of these vectors. Therefore, we have replaced the idea with induced vector by maximal chain. Because of some technical matters, we also added the empty set. And to any permutation, there exists exactly one maximal chain. These sets will be denoted as C sub 0, C singleton is C sub 1, and so on. This also holds in reverse. That means that to any maximal chain, there exists a permutation which rearrange input vector x in a corresponding way, and it will be denoted as follows. Then we can introduce the maximal chain-based Schocker-like integral, as you can see on the bottom of the slide. We should say that, for example, for three-dimensional set X or basic set, there are exactly 6 maximal change, and therefore we have 3 MCC integrals. In the first step, we have defined this functional in a very general way. That means that there is no assumption on set function and nor binary operation all times. But if we want to talk about the properties, we have to consider that set function is a game. Then the MCC integral is monotone with respect to input vector if operation is non-decreasing in the first coordinate. Also, it is monotone in respect to operations if this condition is satisfied. We can say that the maximal chain-based Schottky-like integral is also homogeneous if operation is positively homogeneous in the first coordinate. And lastly, the value of the MCC integral for 0 vector is 0 if operation all time has 0 as a left annihilator. We can also find the lower and upper bound of the MCC integral if all times is left distributive over plus and if is monotone in the first coordinate. In my opinion, the most interesting property of the MCC integral is the linearity, which holds under the assumption right distributivity and homogeneity in the first coordinate. We should say that if we consider operation to be a product and chain C, which rearrange input vector, this input vector, in a non-increasing way, we have on this side a Schottky integral. But in general, these functionals are not Schottky one. This integral will be the Schottky one if input vector x and y are comonotone. What is the known from the theory of the Schottky integral. The last property I would like to mention is here, this equation, which is true if all times has 0 as a left annihilator and if it is left distributed over plus. If we restrict on unit interval, then we can ask whether the MCC integral is the universal integral, but the answer is negative because the MCC integral is not monotone in capacities. What is the condition for universal integrals? As I mentioned a minute ago, the product-based Schottky integral are maybe a little bit more interesting because there is some relationship to the Schottky integral. We can say that if game is supermodular, then the smallest among the MCC integrals is Schottky integral. And on the other hand, the biggest among MCC integrals is complementary Schottky integral. If we replace minimum and maximum with average mean, we obtain induced Schottky integral, which was introduced by Jager in this publication. We have also motivated by Grabish approach to finding new computational formulas for the Schottky integral via bases and transformations. We remember that any set function may be expressed as follows, where psi is a linear invertible transform and B is corresponding basis. We have B with comma because basis should be redefined in empty set as we show here. Then the MCC integral may be expressed as follow, where via Möbius transform and where I sub A is the smallest index, smallest such index that set A is subset of its largest element of the maximal chain. Analogously, we have the expression for the MCC integral via Möbius transform. And now we should say that the concept of the MCC integral relate to concept given here. It is the CC integral or functional where the maximal chain is replaced by arbitrary chain with length of k, and the first element in this O times product was replaced by conditional aggregation operator, the concept which was introduced by Michal Boček and all in this publication. Okay, back to the MCC integral, we come if this operator is a projection operator. That means that for the maximal chain, here is the singleton, and this aggregation operator must be the idempotent on singletons. This concept is a little bit interesting because it covers some well-known symptometric indices such as Hirsch index and lower 2H index, which was introduced by Messier and Gagolewski. And in the future, we also would like to describe or cover with this concept the iterated Sugeno integrals. Also, we would like to introduce a new symptometric index which take a number of authors into account. But now back to Honda's article. The authors also wanted to extend Honda's functional to real-valued input vector. And in the article, we can find the sentence, we can do the same for the asymmetric Choquet integral by applying the resorting to the negative of the vector x as well, and so on. But it is not quite clear because we know what to do with input vector, but there is a question what to do with input vector y and measure and so on. And therefore, it motivated us to find all possibilities how to extend our MCC integral for real-valued inputs. There is 64 possibilities, but column A and B differ only in sign. And also we can say that 7th and 8th block are equal to 0. Therefore, there are 24 functionals. We also should say that functional in one box give the same results because of this proposition. The MCC integral with respect to chain and game is equal to the MCC integral with respect to complementary chain and complementary game. Back to product-based methods, then functionals in the first boxes are the symmetric Choquet integral, respectively. We have the various expressions for symmetric Choquet integral. In the second boxes, we have asymmetric Choquet integral. In the fifth, complementary symmetric, and in the sixth, asymmetric complementary Choquet integral. Functional in the third and fourth box are some combination of these well-known functionals. Also, we have studied relationships among these functional in the table with respect to operation, general operation. And we can say that, for example, if a measure or the game is additive, functional in the first, fifth, sixth, and second box merge into one functional, or for example, if we compute functional in the first and in the sixth boxes with respect to negative input vector, and operation, it has 0 as a left annihilator. Also, this 8 functional merge into the one. So I think it's all, and I thank you for your attention.
Thank you very much for interesting talk. There is some question, remark. No question, no remark. Maybe I have one question. What was the motivation in Honda's paper to introduce like some Y vector according to which there is new ordering and determination of the sets or subsets that are measured? Do you know?
Yes, the motivation was finding some relation, as relation, and
Yeah. Uh-huh.
they need this operator or functional for prove some theorem, but
Uh-huh.
we also prove it without this concept. So,
Okay. Fine. Other questions, remarks? If not, thanks once again. Now we have the last talk of this morning session, which will be provided by, now, I don't know, Barbara Henelová. And the title of this talk is On Conditional OVA Operators. Please take the floor.
Chairman, for the kind introduction. Dear ladies and gentlemen, let me present you our work dealing with conditional ordered weighted averaging operators. OVA operators were introduced by Ronald Jager more than 30 years ago. This article has almost 10,000 citations, and the OVA operators have about 1,160,000 results on Google. OVA operators are a very simple but powerful aggregation tool, and they are applicable in various areas, for example, in decision making, data mining, and image recognition, and many others. But what is the OVA operator? OVA operator is defined as a product of norm weights and rearrange components from the highest value to the lowest one. This mentioned operator covers a wide area of aggregation operators, for example, maximum, minimum, or arithmetic mean. OVA operators have a lot of extensions and generalization. The first, very natural and often used generalization, is generalization using the idea of quasi-arithmetic mean. In this case, using generating function, we can generate a lot of generalization of the OVA operator. The second is weighted OVA, which combines weighted averages with OVA operators. The vector P plays the same role as the weighting vector in weighted means, and vector W plays the same role as the weighting vector in OVA operators. The last but not least generalization is so-called induced OVA. And in induced OVA, inputs are rearranged with another variable called induced variable. So what is the connection between Schoke integral and OVA operator? The starting point of the whole work was this theorem, which states that OVA operator, every OVA operator is Schoke integral with respect to fuzzy measure, symmetric fuzzy measure, and vice versa. The Schoke integral is OVA operator, where the weighting vector is defined as follows. Due to this theorem, the class of OVA operator is a subclass of Schoke integral, and and the OVA operator has also a lot of integral-based generalization. For example, generalization based on universal integrals, scopula-based integrals, and decomposition integrals. So our aim is to develop further, but also useful extension of OVA operators using current research on conditional aggregation operators and integrals based on them. To define the new class of OVA operators, we need three components. The first component is conditional aggregation operator. Conditional aggregation operator is a map which satisfies the following condition. The first condition expresses the monotonicity of conditional aggregation operator only on conditional set. The second is if we have zero values outside of conditional set, any added information will not change the value of conditional aggregation operator. There are some basic examples, for example, minimum, sum, product, or several fuzzy integrals like Schoke, Sugeno, Shilkret, and many others. A collection A is called a family of conditional aggregation operator on epsilon. The second, what we need is generalized level measure. But how we get from level measure to generalized level measure? Considering non-negative vector and fuzzy measure mu, we aggregate information hidden in X and mu by the first line. We measure a set of indices E for which the ith component of the vector is greater or equal to A. The second line expresses the same in the form of conditional aggregation operator. We are searching for supremum of a measure of set E for which minimum is greater or equal to A for set E belonging to the power set. Now we can easily replace minimum with conditional aggregation operator and sigma algebra of all subset with collection. And that is the generalized level measure. Next, some example. Take the minimum aggregation operator and input vector x and fuzzy measure mu given by the table. In order to generalize level measure to be well defined, we assume empty set in a collection and value of aggregation operator at empty set to be infinite. There is a visualization of standard level measure. Next example is when we replace a minimum aggregation operator with arithmetic mean. Input vector and fuzzy measure mu do not change, but as we can see, the visualization of the standard of the generalized level measure has changed. But the question is, how does the generalized level measure relate to the level measure? If we have a trivial collection containing empty set and basic set, then the equality holds only for an idempotent conditional aggregation operator, where on the right-hand side, is well-known level-dependent level measure. But if we don't have a trivial collection, the equation is true for any vector and any fuzzy measure if and only if we have a minimum aggregation, conditional aggregation operator. So the part B claims that both concepts coincide only for the minimum aggregation operator. The third and the last component that we need for definition of conditional over operator is generalized Schoke integral. Generalized Schoke integral of vector x with respect to me is defined by this formula, where on the right-hand side is improper Riemann integral of non-increasing function. When we consider a minimum aggregation, conditional aggregation operator and power set as a collection, the generalized Schoke integral is only the standard Schoke integral. There we can see some computational formulas when we consider the following ordering of the values of conditional aggregation operators. For the greatest normalized monotone measure, the generalized Schoke integral is reduced to maximum over set E from conditional aggregation operator. For the smallest normalized monotone measure, the Schoke integral is only a conditional aggregation operator on basic set. So, conditional over operator. Since the standard Schoke integral with respect to symmetric measure is over operator, the generalized Schoke integral with respect to symmetric measure can be understood as a new type of over operator. A special case of this conditional over operator is a classical or standard over operator when we consider a minimum aggregation operator and add as collection the whole power set. Over operator, the standard over operator, possessing the properties like monotonicity, symmetry, positive homogeneity, shift invariance, and idempotency. But conditional over operator possesses only the properties under the corresponding properties of A, namely monotonicity, symmetry, homogeneity, shift invariance, but not idempotency. So idempotency of conditional aggregation operator is not a sufficient condition, and we need to require that the collection contains a basic set. In the following, we present some explicit formulas for computation of conditional over operators. The first representation is for special collection. This special collection containing at least one set of each cardinality, and the family of conditional aggregation operator is non-increasing with respect to cardinality. Then the conditional over operator is only the standard over operator of aggregated vector. But when the collection does not contain at least one set of each cardinality, or the family of conditional aggregation operator is not non-increasing with respect to cardinality, our formula for conditional over operator will be more difficult. Some remarks. To calculate the over operator on power set, we can simplify the process by first rearranging the vector in non-increasing order and then consider only this collection. When we return to our expression of conditional over operator, we can notice that since the vector v of cumulative weights is determined by symmetric measure, the expression represents max plus transformation of the symmetric fuzzy measure on collection. This max plus transformation is where was introduced by Tora. And this provides an idea for further generalization of our conditional over operators via max-plus transformation of symmetric fuzzy measures. Furthermore, we present some simple properties of the conditional over operator. The first proposition tells that value of conditional over operator lies between conditional aggregation operator on basic set and maximum over set E from conditional aggregation operator. When we have a family of conditional aggregation operator which is non-decreasing with respect to sets, then the conditional over operator is only a conditional aggregation operator on basic sets. So non-decreasing family of conditional aggregation operators are uninteresting for us. An interesting question is if a conditional over operator will be an averaging operator. And this is true only for an idempotent family of conditional aggregation operators. When we have a space of size 2, then over operator, this conditional over operator is only the standard, is only the convex combination of its extreme values. It has been proved that the generalized level measure can be rewritten using transform of fuzzy measure to hyperspace. This is work of our colleagues from Košice, and this provides an interesting viewpoint of the generalized level measure is only measure-to-measure transform of standard level measure, and this theorem arises in question whether the conditional over operator is the over operator of the transform vector with respect to transform measure. More precisely, whether the transformation of symmetric measure is symmetric again. As we will show in the example, this is not true in general, and thus for this transformation theorem offers another kind of generalization of conditional over operator. And I would like to present or illustrate a numerical example in decision making involving selection of strategies. Our analysis centers around an economic issue concerning country monetary policy. And the government has 5 options: develop a strong expansive monetary policy, develop an expansive monetary policy, do not develop any change in the monetary policy, develop a contracting monetary policy, and develop a strong contracting monetary policy. To evaluate these strategies, they have assembled a panel of experts, and they evaluate these strategies or consider another options, namely very bad economic situation, bad economic situation, regular economic situation, good economic situation, and very good economic situation. The outcomes are displayed in the table. And in this scenario, the experts make use of the following weighting vector. So in the next table, we can see aggregated results for different types of over operators and different types of conditional over operators. In the next table, we can see ordering of options based on the result from previous table. We can see that classical OVA or standard OVA does not distinguish between option A3 and A4. But for example, OVA operator prioritized option 1 A1 before A2 and A4 before A3. Our conditional over operator, when we consider arithmetic mean and Choquet integral, could distinguish between all options. And when we consider the conditional over operator with Choquet integral, it can be seen as a two-step evaluation, for example. And the choice of strategies highly depend on the choice of the conditional over operator and also aggregation operator. This is all from me. Thank you for your attention.
Thank you very much for a really interesting talk. There are some questions or remarks. No? Oh, nobody can help me? No. So maybe one question. So you said that there are many generalizations of over operators. There are some of them that can be expressed using this approach, this conditional over operators, because there is also some G function. So maybe this G function is not aggregation,
Yes.
but
Yes, it could be possible, but I don't know. We don't try this. It's a good question.
And also I see some methodological problem because we see that the decision making can be, or the result for the decision making can be evaluated using different approaches of operator and so on. And there is a methodology which is the best, or we can combine more to find the best solution of this decision making problem. Did you think about something like this?
More like theoretical,
Okay.
not applied work.
Okay. So other questions, remarks? If not, thanks once again. And because this was the last talk, so this session is over. I wish you good lunch and enjoy the free space before the afternoon sessions. Thank you very much.